If you have ever generated an image with Nano Banana or GPT image, you have watched a generative AI model turn pure noise into something beautiful. But here is what most people don't know. Nearly every generative model, like diffusion, VAEs, normalizing flows, and others, trace back to a single equation. And that single equation was written by Ludwig Boltzmann in 1877 to describe how gas molecules arrange themselves in a container. What separates these model families is just one thing: how they deal with the hardest part of that equation. In this video series, I'll teach you the most radical member of the family, called the energy-based models, or EBMs. The surprising part is that EBMs are not just generative models. Many machine learning and deep learning models can be expressed as EBMs. So they provide a unifying framework for machine learning and physics. In this video series, I will go through this Jupyter notebook to first introduce the concepts and define EBMs. Next, I will briefly discuss how linear regression, logistic regression, and fully connected neural networks can be expressed as EBMs. Next, I will get into the modern use case of EBMs as generative models. First, I will explain the concepts through simple to understand examples. Then, I will get into the so-called deep EBMs, which uses neural networks for training and generation. I will implement a generative EBM in PyTorch to train using handwritten images and generate new ones starting from noise. In this last part, I will discuss methods such as Markov chain Monte Carlo, Langevin sampler, and training tricks like persistent contrastive divergence, and how all these connect to physics. This notebook is mostly written from two references, one by Jan LeCun and colleagues, and the other by David Carbon, if I pronounce their names correctly. Since recording and editing these videos take a very long time, I will cover the entire notebook in a series of videos. Hi, I'm Erdogan. I have a dual PhD in physics where I developed a new mathematical model for the theory of gravity and also collaborated with the CMS experiment at the Large Hadron Collider, working on extracting meaningful patterns from their terabyte-sized data. After my PhD, I was a data science fellow at the National Library of Medicine. And right now, my focus is on new AI models inspired by physics and finding a mathematical framework that unifies physics and intelligence. All right, let's start this course by defining energy-based AI models. Imagine a gas of molecules in a container held at a constant temperature T. If you take a picture of the container, you will find the molecules in a particular configuration. In statistical physics, the probability density of finding this gas in this configuration is given by the following equation, where U is the total energy of the container. Z is called the partition function and is actually a constant. Its job is to make sure that the sum of the probabilities is equal to 1. The main difference between all generative AI models is in how to handle this C. We get back to this later. For now, let's discuss the physics side. This same equation describes the probability density of any other physical system held at a constant temperature. For example, if we are dealing with a magnet made of atoms that can have spins up or down, shown as black or white pixels in this animation, the total energy of the magnet will determine how the spins arrange at a given time. For example, it is this equation that tells us that if the temperature is high, this animation will never show all white or all black pixels. But if we reduce the temperature, at some point all white or all black pixels are actually highly likely. Interestingly, this same equation can be applied to most non-physical systems due to something called the maximum entropy principle, which is the counterpart of the second law of thermodynamics. You don't need to learn these principles and laws in this course. Just memorize the form of the probability density function and one condition. The system we are trying to model with this equation should not have been interrupted by a major external factor. For example, This equation cannot explain the housing market when it has recently crashed due to a depression. Let me explain what I mean when I say the probability density of a non-physical system is given by this same equation. Imagine you have a dataset consisting of house properties and prices. Each row of this dataset is a configuration of the housing system, just like each image of the gas container was a configuration of that system. That means the so-called energy of the housing system is a function of one row of this dataset. Note that X here is a vector, which means an array of the columns of the dataset. Let's assume our dataset has only one column, which we refer to using X. We also assume the energy of our system has the following form. In this plot, the y-axis shows the energy. The x-axis shows possible rows in the dataset. If we insert this energy into the probability density function and compute z using the following equation that ensures the total sum of the probabilities is equal to 1, then I can also plot the probability density of this same system. If you compare the locations of minima of the energy with the maxima of the probability density, you will see that they happen to be exactly at the same position on the x-axis. Since the maxima of the probability density are just the most likely configurations of the system, that means most of the rows of the dataset happens to be very close to these two locations. And that is mostly the concept behind EBMs. Now remember that I told you the difference between generative AI models is mainly in how they handle the normalization constant z. EBMs handle it by throwing it out. Instead of directly calculating a probability, an EBM assigns a single scalar value called energy to every possible combinations of variables, which are the configurations of the system, or simply speaking, the possible rows of the dataset. If the energy of a configuration is low, the set of variables is highly compatible, and the configuration of the system is highly likely. If the energy is high, the variables are incompatible, and that configuration of the system is unlikely. The other member of the family of generative models that avoids computing the partition function z is the diffusion model, which is, as of today, the most commercially used generative AI model that everyone gets to utilize when working with Google's Nano Banana or OpenAI's GPT-Image2. The main advantage of EBMs and diffusion models is that they avoid solving incredibly difficult, sometimes even impossible, high-dimensional integrals in the definition of Z. The disadvantage is that their use cases become limited. Certain types of tasks require the full probability description of the system, which means we need to switch to models that estimate Z. So finding an elegant method, just like how people found the backpropagation method that efficiently computes Z, can be a breakthrough in the field of generative AI. The problem is that Z is almost equal to infinity. So we need to break this infinity into an infinity plus a finite number. And that is what high energy physicists have been doing since the 1940s, when they developed regularization methods to extract meaning out of infinities of this same partition function z. With this, I conclude part 1 of the EBM video series. And one last thing, if you enjoyed this material and want to go much deeper, I run a mentorship program where I personally guide people through physics-based AI models. In this program, you get a personalized roadmap built around your goals, and you get direct access to me for questions and suggestions along the way. If you have a STEM background, know some Python, and can commit at least 5 hours a week, book a short alignment call to discuss your current level and your goal. The link is in the description. Also, I have a few favors to ask. First, share the videos in your communities and with friends who might be interested. This will be the most effective way to support me. Also, please write your suggestions and questions in the comment section so that I can adjust the videos as we move forward.